So can you hear me speaking? Okay, let's wait until uh, wait for a few minutes. I think there are someone that will be a bit late. Okay, let's try again. Can you hear me clearly? So let's start today's talk. Oh, So today we are going to treat with the main part uh, of McDermott Solomon's Appendix C. So it is the generalized Riemann-Roch theorem, and we should do some preliminary work in order to introduce to what happens. So we are going to do some preliminary work in order to introduce formalize the whole statement of the generalized Riemann-Roch theorem, which is uh, some differential geometrical notions. First, we set sigma to be a compact Riemann surface. With boundaries. And we let E to be a complex vector bundle over sigma. And we assume it is smooth. And also we fix a complex structure or almost complex structure on sigma. So uh, So we want to introduce the first order differential operators and also uh, then the Cauchy-Riemann operator on the Riemann surface. So we first give the definition. The first order differential operator seems to be a combination of vector field and anamorphism. There are many equivalent definitions. One is the global session. of the bundle, which is the tensor product of E and D1, where I think we need to say of the yes, bundle and shift are so bundle E tensor with D1, where D1 is the direct sum of the vector field on sigma and the trivial bundle C. So it is Lie algebra. Generated by a vector field on sigma and scalar functions. So we want to set D1 to be a direct sum of the vector field and scalar functions because we want to introduce non-homogeneous terms. So if the scalar function is D1, if D is in fact in a vector field, then if the tensor product with a vector field and E, then we say D is homogeneous of order 1. And if we have order 0 terms, that is D will be like the tensor product of X plus some matrix A and tensor with S, where S is the global section of E. Then D is not homogeneous. Equivalently, this can be formalized by differential form. So we can view D as an operator from omega 0 at sigma E to omega 1 sigma E. Here we set omega 0 and omega 1 to be the set of global sections of the tensor bundle T sigma tensor T star sigma tensor with E. And omega 1 to be the global section of the bundle T. No, this is just the global section of E. And this is the global section of the T star of sigma tensor with E. So we can view D as a first order as a we say it is sigma. It is it is the infinity linear function, the linear map, and such that it is a first order derivative of no. We can say it is yes, it is just C infinity linear map that maps omega 0 to omega 1, or we say it is omega star to omega star. The direct sum of all of the differential forms on E, because we have given list of the omega 0 to omega, no, it is not omega 0 to omega 1. It is only true when it is homogeneous. So equivalently, it is only a equivalently it is the total differential form from E that is a C infinity linear map. And here we say we set this to be the direct sum of all the differential forms of K. And this is the tensor product with tensor product of the differential form with E, such that uh, if we can decompose D into different parts, we have a homogeneous part. So we set the first order part to be simple. Then how can we write a symbol? The symbol of D will be from omega 0 to omega 1, or omega k to omega k plus 1. So it's order 1, it leaves the order by 1 with a derivation. And in fact, we know that it is given by vector field. Okay, so what are we going to say? What are we going to say? Oh, yes. So why is this case? Yes. So recall that a connection on E is a C infinity linear map from E to the omega 1 of sigma, and from the global section of E to the global section of the tensor bundle with values in the endomorphism, such that no, it is just any C infinity linear map from the global section of E to this, because we know that a connection will be given by a connection form alpha. And for any S in the global section, we have the connection of S belongs to the global section of X, and with it's a differential form with value in E. And we must have for any X in the vector field the true connection must be given by, firstly, I think if we have Fs must be given by Xs, a function, times S plus F times how do I say? Yes. So this is given by T as X X on X plus alpha X on X and X on S. So ds is a differential form with values in E. Differential one form, if I say it is a differential one form with values in E. And we know that in this case we have in this case for any x, a vector field, the connection with x is a differential operator of first order. Uh, I think, yes. Uh, yes. So, yes, because we know that dxs we can view it as x cancel with s uh, plus alpha of x times with x. And this is the same as this because we know that a differential operator will map any section to the tensor bundle, and this acts as the first order term, and this acts as the zeroth order term. And in fact, if we could, and in fact, we can act act on x, we can act on s such that, so we can act on s such that locally we have write s as a vector value function, and then this will be just the derivative, or there will be a linear combination of all this, so this will be x1 and then 2x1, but the things are the same, that it is in fact taking derivation, and it is a zeroth order, so this is a matrix. So this gives us a point of view of what a differential operator on a vector bundle looks like. What happened? Oh, okay. So on the other hand, sigma is a Riemann surface, so it is a compact manifold, and we can decompose its tangent bundle into the direct sum of the cotangent bundle into the direct sum of two different parts. One is 1, 0, and the other is 0, 1. That is, since we have a J, so this is since we have a complex structure J, so this will correspond to eigenvalues, eigenspaces of J. So in this case, we have a natural differential operator on the Riemann surface sigma given by, firstly, from sigma to the space of differential operators. No, what is that? First from functions to function. Yes, this is the omega 0 of sigma to omega 1 of sigma, the differential form, and then we project it onto the 0, 1 form. No, to omega 0, 1. This is the global section of the space of 0, 1 form. and we write this composition to be d bar. And this will be a first order differential operator. On sigma, which is very natural because we know that this projection is just the standard d bar in complex geometry. So and now we can give a definition of the complex linear Cauchy-Riemann operator. In this case, we add the adjectives complex and smooth to mean that it has smooth coefficients and it is complex linear. But we are
sorry, excuse me. I'm a little bit confused by your definition of connection.
Oh, okay.
So why is it mapped to the forms with value in the morphism of E? I mean,
because
it should be itself is a section, but it's not a map from the sections to the endomorphism. So you can take.
Yes, it is. Yes, it is a section. Yes.
Yeah. So itself is a section of this bundle. Yeah.
A section of.
Yeah, and then you wrote so nabla xs is equal to x tensor s. I'm also a bit confused. What do you mean by x tensor s? So x is a vector field on the Riemann surface, right?
Yeah.
And s is a section of E. So
yeah.
so right now
yes, I mean how to view how to regard the connection with value with vector field x as a differential operator with our previous definition that it is a tensor, it is a global section of the bundle with E tensor with D1. So the D1 will so in order to formulate this, we will we can write the dxs to be the tensor to be in the global section of D tensor D1, and x is in D1, and also alpha x is also in D1. And we know D1 is a direct sum as a tangent vector of sigma and also the smooth function of C. No, it is not smooth function. It is yes, it is a set of smooth functions on C. So so in this way, we know that the connection with a given vector field will give will give a first order differential operator, but we will not use it because there is a natural way to so dxs is in a natural way belongs to the global section of E because we can just remove the tensor product. Or to say we just write it as dxx as first as a differential dx as a vector value differential operator on the tensor on the differential one form with value in E, and then we pair with x. So that is when we tensor with another with the tangent bundle, and then we just contract the two dual bundles to become E. And in this case, we can rewrite the and in this way we can rewrite the bundle as E tensor with T sigma direct sum with the C infinity of sigma and C. So it will become E tensor with the T sigma, and then direct sum with the but we know that C infinity sigma C is the coefficient string. So we know that this is in fact E. No, it is. No. So, yes, it is. Yeah.
Yeah, it is E, right?
Yeah, it is E. And direct sum with E. And in this way, we have also a natural action of the X on E, just as okay. Maybe the screen has some problem, so I cannot move it very freely. Yeah, okay. So there is also a natural way from E tensor sigma to E is given by, for example, the S tensor with S. Then we can write S as a, so it is as just X directly on S, because we know that S has locally.
Oh, okay.
Yeah, so locally is a direct sum. So of direct sum with R. So and then we just X on S to become another to itself. So it becomes, and then we add them together to obtain
Okay. Okay, I see.
So it is very weird because the first order differential operator is defined in such an abstract way. So I think it is new to me when I first read this definition. It is given in the in this book. Calculus.
Okay. It doesn't seem to be like a very common definition of differential operators.
Yes, it should be a very common definition. And this explains how the connection is differential operator in a natural way. So we say a complex linear, a complex move Cauchy-Riemann operator is a first order. First, it is a first order differential operator. E on E, such that when we for first order differential operator, we can also project it onto the space of 0, 1 form, just as no. So such that for any S in the global section of E and also F in the global section of sigma, we have the following Leibniz rule. So we must let the 0, 1 part of B to be the standard one. I think, oh yes, this should be Fs, because there is a natural way. Yeah, okay. So plus D bar F tensor with S. In fact, it should not be a tensor because yes, that's right tensor. It should not be a tensor because CS is again a section. So it is just multiplication by coefficient. So we know that it should be a standard. So we know that it should be standard on coefficient. But even if it's standard on the coefficient part, it is not necessary that it is unique. In fact, there are many of them, and we can construct them again via connection. Let us write abbreviatedly CR operator. So in this, so now we must introduce another thing called the emission structure in order to construct such a Cauchy-Riemann operator, because with an emission structure we can can decompose uh, yes, there are some problems with my computer. Okay, so we then introduce the emission structure. So if to the complex vector bundle over some complex manifold X, and we set the emission structure what happens? No, there. Oh, okay. I see there are some discussions. No. Oh, okay. The emission structure. Oh, E is a C infinity of X C linear bilinear mapping. In fact, we must be to say that it is we use some shift notations. So it is AX linear mapping. AX bilinear map H from the space of E tensor with E to E is the sheaf-off section on E to AX such that, and we know that it can be determined on any tangent cotent on any fibers. So HX from EX to EX is in fact a vector space tensor with EX to C is an emission inner product. Yes. For this emission inner product and the complex structure, let us recall the complex structure on E. We know that there exists emission structure on E that is compactable with J, that is such that J is orthogonal. In fact, we are firstly introduce real inner product and then try to construct another. So such that J is orthogonal or to say compactable with J, then yes, then we say a connection on E is an emission connection if this connection is compactable with J. So we know that such a connection is always exists. The proof is very similar to compatible with J, and maybe we should add some maybe we should add the so-called torsion torsion property. But such a connection always exists, and the proof is very similar to Liouville connection. Because we just write local coordinates, and then we solve linear equations. And in this case, it is not unique. It is not necessarily unique, but we know that when we introduce a homomorphic structure, then there is a conjunction. So we do not meet with homomorphic vector bundles here. And we know that with an emission connection,
excuse me.
Sorry. Okay.
The Levi-Civita connection only makes sense when E is tangent bundle.
Yes. When E is tangent bundle.
E is also tangent bundle. You say the second torsion.
No, yes, there is no torsion torsion condition. Yes, there is only that is it is compatible with J. That means that EH. No, I think this is mean that yes. D equals to connection with S1, S2 plus. Here we use the real part because we know real part is also an inner product. So it means that there is a Leibniz condition, and here, although we have although it is in a differential one form, but we know that we can view it as a tensor product of T star sigma with E, and also another section is also a section of E. So we just use H, identity tensor with H to obtain T star sigma. So this will be a differential form, and this is again a differential form. So they are all differential forms. Or you can say with a vector field X, we have X on the. So we write the real part of H to be the inner product. Then we have X on the inner product to be this plus another. So this will be much like the notion that it is compatible with the metric. So we can also construct Cauchy-Riemann operators from this emission connection, because we can just take since this connection is an emission connection, we can just take the 0, 1 part. Then this will be a Cauchy-Riemann operator. This is because the connection is just a global section to the differential forms of the global section. And then we can, so this is the T star of sigma tensor with E. It has a natural split into, Dirac sum decomposition. So we can just project it onto the 0, 1 part of the differential operator, and this will give the corresponding connection. Just say 0, 1. So it will not be a self-order. It is again a connection, but we can make. Let me see how to. Yes, yeah, it is just a connection. Will be a scale operator on E. Okay. So it can be easily verified because we just need to verify the definition that it must be standard on the space of global sections, so that it will be a complex remove the Cauchy-Riemann operator. But this follows from the Leibniz rule of the connection, because you know that the sigma 0, 1 to fs will be equal to first x on f and times with s plus f and times with this will be a tensor product. So the second term does not. So we only need to see what happens on the first term. So we know that f is in the f is a global section. So this gives the how to say? Yes, f is a function. So this tells us that this will be a and also this must this tells us this must be only the 0, 1 part 0, 1 differential form of 0, 1 type. So if we need to and also we know that the connection is trivial on sigma. Yes. So we know that this is given by df plus alpha and tensor with f, where df is here we do not need tensor product, so this is just f alpha, where alpha is the connection one form. On connection one form, where it is endomorphism of E, but now we are treating with F, so it must be an arbitrary connection one form. So it must be just a differential form, one form. And when we project it, it becomes alpha 0, 1 and to d bar of F. And in this case, this should vanish because in this case, there should be no one form. So yes, because it is because the connection should be a linear, so the action of the connection on F should be directly equal to d bar of F. Since this is just the standard connection.
Excuse me. So I just want to make sure I understand in your definition of Hermitian connection, you're using the real parts, and I mean this is equivalent to if you drop the real part, just using the entire complex numbers. I mean this real part is with respect to a fixed, almost complex structure. Complex structure J, and that J is determined by the Hermitian structure H. Is that right?
The Hermitian structure consists of an Hermitian inner product with a given J, and the J must be compatible with the yes. So with the Hermitian structure it's just intuitively it should be a complex linear and complex antilinear. With the first variable is complex linear and the second is complex antilinear with respect to the to j. That is, if j acts on here, then then we should there will be a minus on here and I.
Right. I guess my question is,
Yeah.
I think what I learned about Hermitian connection is the definition without using the real part. Is it equivalent to that one? So like it's dh of S1 S2 is equal to h nabla S1 S2
yes,
plus h.
yes,
Is it they're the equivalent, right?
Maybe there should be some connection. There should be some conditions that should be added to this. I think. Oh yes, if we require no, if we cannot require this. So the image of each. So the second one is the form. So, it should be equivalent in the way that the connection. Yes, it is a very fatal question. I think we should add some conditions to the connection nabla if we require the if we only use the real part of the of H. But we know that this condition, if we have this condition, then since we know that D and also we know that D is in fact real. And also the connection is required to be a sum of a connection is intuitively D plus alpha, where alpha is a complex linear differential form, so that it will be so that this will imply the real part. Will be implied the Leibniz rule for the real part. So, okay, yes. If we require it to be complex linear, then the condition will be equivalent. So, condition connection compatible with REH, and it's complex linear. What is meant by complex linear? Yes, it should be complex linear. That means that sigma with A plus with S1 plus JS2 is equal to sigma S1 and plus J sigma S2. That we require it to be complex linear. So in this case, I think the definition will be equivalent. And conversely, with such a emission connection, H and a complex linear Cauchy-Riemann operator T, we can find a connection T such that emission connection such that C is in fact comes from this connection. So we know that this is we do not lose any information by associating to an emission connection on the vector bundle, because all complex linear Cauchy-Riemann equation operators come from such a connection. And we would like to introduce the joint operator. So a joint operator means that it is adjoint to the linear Cauchy-Riemann equation, the complex linear Cauchy-Riemann operator with respect to some inner product. Defined on the space omega star of sigma e. So this is defined via integration. That is the L2 inner product. So we must introduce the Hodge-star operator in order to form the inner product and also the Hodge-star operator star defined on the base of all differential forms such that it maps omega to the orthogonal complement star omega, where if omega is in sigma k, then omega k, then the orthogonal complement will be in omega of n minus k. And in this case, we are treating with Riemann surfaces, so there is only omega 0, omega 1, omega 2. And omega 1 decomposed as omega 0, 1 direction with omega 1, 0. And the Hodge-star operator will map from omega 2q to omega n minus p n minus q. And we know that there is if in a local coordinates there will be a frame of differential forms, that is ds and dt, where z equals to s plus it, and we have Hodge-star operator f from ds to dt and f from dt to minus of ds in the standard. So it is, yeah. And there will be associated a volume form on sigma. So with Hodge-Star operator, we can associate any differential form to associate any two differential form of the same degree to if in sigma, and we can associate to a number which is integration over sigma of omega wedge star of beta. This gives a linear pair. This gives a pairing, and we know that in the cell duality, this pairing is used to define the non-degenerate bilinear pairing to obtain the isomorphism between one cohomology to the dual of another cohomology. So in this case, we have two sections we have two vector values differential forms, like omega tensor with S. So we can say the pairing eta tensor with T to be the product. And then in the to be the product. And then we just integrate them, that is integrate over sigma of omega tensor S and eta tensor T to differential forms and with respect to the volume form. Notice that for a different choice of the emission structure, the volume form will be different. Like they will not be the volume form should be the volume form will be different. That is no, the volume form is the same. Yeah. So with this Hodge-Star operator, we can define the formal adjoint operator of the Cauchy-Riemann operator. Of the CR operator sigma to be nabla to be
excuse me.
Oh, okay.
I think in the last there is no volume form because it's already top degree. Have wedge with hot dew.
Oh, okay. Oh yes, this is just integration. Yes, this is integration. Yeah.
I'm quite confused about you say the volume form on sigma, is that ds wedge dt?
ds wedge dt. Yes.
But the transition function between two holomorphic coordinates is a conformal transform, right? It
yes.
does not preserve the volume form. So I'm quite confused about the Riemann geometry definition of the Hodge-Star and the complex geometry definition of Hodge-Star.
Oh yes, they should. Oh no, they should be the same because we should. Let me clarify this. So this is no. So there are some problems with. I think we should. Yeah, I think we should associate another emission structure on sigma. We should associate another emission structure on sigma. That is yes. So hostile operators often associated emission structure on sigma. So then we can talk about the orthogonal complement, and so and we have DSTT must be an orthonormal basis. Then we must then we will have DS. Then we have the relation between DS and DT. But there is another problem in the following. So let's just move on and see what will happen. What will happen in the following. So then we have a linear pairing, and we just associate the formal adjoint operator to be just like what we have done in differential geometry. Good. Then this will be an operator from omega 01 from 01 form from E to 0 form from E to global sections of E. That is given by and from this we know that the integration of S and T of two vector value differential forms and with one no it is deep yes the vector value of two differential forms the integration over this is equal to sigma with the adjoint operator acting on omega and pairing with S. The integration. So we know that this is true. This is a true formal adjoint operator. And if we want to see what it will look like, we should pass to the local coordinate. So again, we let uj be a local coordinate to j equals s plus it, and with ds dt orthogonal. Since they are related by complex structures, so any emission product will give this as an orthogonal basis. And then in this case, with an emission connection on E, the emission connection of S and the emission connection of T can be computed directly as the vector field plus first order term phi, and T as the formal sum as the sum of the vector of the differential operator of a vector field dt plus the matrix psi. And then we can compute the d bar, the Cauchy-Riemann operator to be it should be the 0, 1 part of the of the connection, which is just 2/1 of yeah. So we can firstly compute the nabla itself, and when it's acting on any section, here we must use C because there are ft here, so we must change it to change the notation for section. So it will be ds to c ds plus dt to c dt, and when we yes, and so when we pass to the 0, 1 part, this will be 2/1 and c to c plus j times c to c, and compose it with the complex structure on the Riemann surface, and which will be written as ds minus I dt, which is d bar, dz bar, and in here we have ds of the c plus or minus plus j of dt to c, where j is the complex structure on E. And in fact, in local coordinates, we can identify it with I, just multiplication by I. And so we can compute it, and this is just the D-bar operator. And the formal adjoint acting on any function f, act on any differential zeta of dz bar, it will equal to the associated adjoint dz bar dz zeta of dz bar, and which is equal to minus of, and dz bar should be identical, and dz bar is in fact ds plus idt, ds minus idt. So in the the Hodgson operator will map it into what happened? We'll map it into ds zeta, and ds minus idt becomes ct minus ct plus ids, and which becomes yes, the final result is which becomes ds zeta ds y dt plus I times dt zeta minus I times dt zeta dt ds, and then we take the 0, 1 part. No, there are no 0, 1 parts. Yeah, this is the no. We should use the d bar. We should use d instead of d. Yes, here we should use d instead of d bar because well, oh yes, d is just another part which maps d0 to d10, and then we can map d01 to d of d2, d11, that is d2. So, and finally we obtain the from, and we obtain the minus ds to c plus I dt to c. So we have for any theta delay a differential 0, 1 form. We have -2 of d theta, or we say it is a conjugate. It is conjugate of this operator because we need to change the minus sign to a plus, change the plus sign to a minus sign, and then obtain the same result. So this is a local computation. So there is a problem that in Murdoch-Solomon's book he uses he associated volume form that is lambda square of ds and ds for ct, by ct. Okay, I know I know the reason. So even if we have yes, even if we have ds by ct of a gonal, we cannot say that ds by ct is the volume form, but the volume form may be ds ct times lambda square, where lambda is in S1. Why is it just this? No, it's very strange. So, now I don't quite understand why the lambda square of ds by dt should be why he uses the volume form. And then he will obtain that this will be there will be a parameter here. This is lambda minus squared, and then the result will be there will be a minus lambda minus squared in here. Okay, so finally we can we can move into the definition of the real Cauchy-Riemann operator. Real linear and non-smooth. It is real linear because it is not complex linear because in our usage we are always linearizing a real operator that is called the nonlinear Cauchy-Riemann operator over the vector bundle. No, a nonlinear Cauchy-Riemann operator from a curve to some symplectic manifold. So we need so when we take the linearization, it is not necessary to be a complex linear and smooth Cauchy-Riemann operator because we are not even concerning sections, concerning smooth sections. We are concerning sections in Sobolev spaces. So we have let me see. So we first consider the space of all omega. We first consider space of all omega, sigma, and Ex. So let me so we need to consider the real linear case that is not complex linear, and also it is non-smooth. That is its coefficients are not always smooth, but in some Sobolev spaces. So we have firstly we say a bundle of E is real, is totally real. If we have F, the conjugate of F is equal to F. The conjugation is obtained by J, is obtained from J. So we have a bundle pair EF with F is a vector bundle on the boundary, and F is totally real. If E is symplectic, then F is a Lagrangian subspace. Lagrangian. That is, every point is a Lagrangian subspace of E, or to say a Lagrangian distribution. Then we can say that there is almost complex structure such that F is totally real. So it will fit into our setting, and we can define it, and we can define a generalized PQ, a restricted spaces, a restricted space of sections of differential form. That is a set of differential forms such that it has a boundary condition. It has a boundary condition. Omega restricted to the boundary is in fact in the totally real subbundle F, and we say WKP F of sigma E, the associated Sobolev space of sections. This is so this is a non-smooth space. It is only K. It is only the weakly derived. Okay, so we say EF is a bundle pair. And also we have a real, and then we can define a real linear Cauchy-Riemann operator. Of class WKP. It is a differential operator of the form C plus D equals D0 plus alpha, where D0 is complex and smooth, and alpha is in the section of that is, it is of class W, KP, F, not F. We do not assume a boundary condition, just sigma and E, and tensor with the differential form is sigma star, K star of sigma. No, we must let alpha to be no, just we need to let alpha to be 0, 1 form and tensor with the endomorphism in R, E. So then with such an alpha, C is always not complex linear. But we know that since we only add a 0 order term, it is gauge equivalent. To a complex linear, to a complex smooth Cauchy-Riemann operator. Okay, that's all I have prepared for today. I must apologize that because previously I think that I should spend 3 hours on the first 2 sections, so I do not prepare for the third lecture. for the first talk. So this is so there are many things that I am not quite well prepared. Maybe there are some questions that are not solved here, and I will try to figure it out in the following week. So when we define a real linear Cauchy-Riemann operator, then we have finally completed the final preparations for stating the Riemann-Roch theorem in our case. And there are some questions about this section, about this part. Oh, okay. So the definition is given via the completion. That is, we have a L2 inner product, and we have the derivation. That is, turbulent spaces. Here we are assume we are working on compact Riemann surface. So we will not meet with the difficulty of defining the measure on the non-compact Riemann surface. That will involve some finiteness. Will involve some problems that the measure may not be finite. But here we are working on compact Riemann surface, so any volume form will have finite area. Then we can associate WKP is the compression. Compression of the space. Say if we are working on differential forms like 0, 1, and F, if we have F, then sigma and E under L2 inner product. That is, if omega and eta, then L2 product is just the pairing of omega and eta. It will be will be integration, and then we just compact and we just complete with respect to this and all their derivatives of order up to k. Oh no, there is no L2. It is LP. So we need with respect to LP metric, that is integration over omega and pairing with itself and 2 of p. That seems weird. And yes, you just take a moment integration with respect to the volume form. So this is the usual definition of the turbulent space. That can be seen in like Evans' book or others. We just make a slight generalization of this. Are there other questions? Okay, so if there are more questions, you can send an email to me. And there are still 2 questions that are not that are not solved during this talk, and I will try to figure it out and try to solve it in the next talk, that is next week. And so see you next week.